L. I mean, in any order you can connect, because anyway it is a series LCR circuit. Because it's a series LCR circuit, current through all devices, I mean resistor, capacitor and inductor are the same. Suppose if you apply an EMF E equal to E naught sine omega t, voltage across the resistor will be in the direction of the applied EMF, whereas in capacitor voltage will lag behind, whereas in inductor voltage will lead. Okay, so it is VL. Actually we have already written, since it's a series LCR circuit, all will have the same current. Voltage across resistor is I into R. Voltage across capacitor is I into XC, where XC is the capacitive reactance, and we write capacitive reactance as 1 by C omega. And voltage across the inductor is I into XL. This is inductive reactance. This is I into XL is actually equal to L omega, where omega is the angular frequency of the applied EMF. And see here, if you draw this diagram, like we have this phasor diagram. Suppose in the axis, if applied EMF, okay, let me write applied EMF, and this is the EMF across the resistor, and EMF across the resistor will be along the applied EMF, whereas EMF across the inductor will be 90 degree ahead of this, whereas EMF across the kind of capacitor will be 90 degree behind. We know that. So we call this EMF as EMF E across. These are all instantaneous EMFs. Okay, so in that case you can write this diagram as, since EL and EC are opposite to each other, suppose this is actually equal to Y, this is X, means the net EMF will be equal to Y minus X. So this diagram can be written as, this one will be EL minus EC, and this one will be the applied EMF along the resistor, which is ER. So the net EMF will be the sum of these two. Since these two are 90 degree, so you take this arrow and keep it here, and when you draw this is the resultant EMF. So the resultant EMF will be ER, and this is EL minus EC. So this one equal to root over ER square plus EL minus EC the whole square. So if you write like this, the total current in the circuit, I will be equal to total EMF by total resistance. The total EMF is given as root over ER square plus EL minus EC the whole square. Okay, so this is total EMF divided by total resistance. Let's write the total EMF first. So the total EMF, which can also be written as VR VL. So total EMF E equal to square root of ER square. ER is actually instantaneous current into resistance whole square, plus EL is actually instantaneous EMF into XL minus this is I into XC the whole square. If you take I out, I into root of R square plus XL minus XC the whole square. So then in such case, this is the EMF. So EMF by resistance, EMF by current is the total resistance. So that is equal to root of R square plus XL minus XC the whole square. This is called impedance of the circuit. So here you know the applied EMF E, so that is why we are supposed to find the current. The current I is equal to EMF by impedance, total impedance. So resistance offered by this resistor is R, resistance offered by this capacitor is capacitive reactance, resistance offered by the inductor is inductive reactance. So which means that the total current in the LCR circuit will be EMF divided by root of R square plus XL minus XC the whole square. So the current will be maximum when this is actually maximum. So this one can be written in two ways. Suppose if you want to find out IRMS, this will be equal to ERMS by this root of R square plus XL minus XC the whole square. Similarly, if you want to find out I naught, the maximum current, that is maximum applied voltage divided by root of R square plus XL minus XC the whole square. So these two things. And here also you see, this is the direction of the resultant EMF. This is the EMF across the K resistor and applied EMF are in the same direction. So the resultant EMF makes an angle phi with the applied EMF. So if you have this diagram, suppose this is the EMF across the resistor, along this direction only applied EMF will be there. This is the resultant EMF E, which will be equal to root of ER square plus EL minus EC the whole square, and this one is actually EL minus EC. So this is phi. What about tan phi? From this tan phi, usually angle can be easily found using tan because it is an increasing angle. So tan phi is opposite side by adjacent side. So EL minus EC divided by ER. So I into XL minus I into XC divided by I into R, which means all the i's will be cancelled. So XL minus XC divided by R. So the tan phi or phi is the angle between the applied EMF and the resultant EMF, that is EXL minus XC divided by R. In other words, phi is equal to tan inverse of XL minus XC divided by R. But you know what is XL and what is XC. So let me write phi, angle between the applied EMF and the resultant current also we can see. Between the applied EMF, and because current is EMF by this resistance, no, so EMF and the resultant current in the LCR circuit, phi is equal to tan inverse of XL minus XC by R, but XL is L omega, XC is 1 by C omega divided by R. Like that you can write phi, you can write IRMS, ERMS and all those things. So we have here applied an EMF E equal to E naught sine omega t. As a resultant, it develops a current I is equal to I naught sine omega t plus or minus phi, where phi is given by this relation tan inverse of L omega minus 1 by C omega. If 1 by C omega is greater than L omega, then this value is negative. Here it is going to be omega t minus phi. If L omega is greater than this, suppose if XL greater than XC, then in such case I equal to I naught sine omega t plus phi. Okay, I mean, because when inductor is more, this is more than this, means omega t minus phi. When the circuit of capacitive, that means XC greater than XL, in that case I naught equal to sine of omega t plus phi. So where phi is the angle which is tan inverse of L omega minus 1 by C omega into R. So let us come back to this thing again, the maximum current or RMS current in the circuit. So here I is equal to, or I naught, the maximum current, I naught equal to E naught by square root of R square plus XL minus XC the whole square. So this I naught will be maximum when inductive impedance is minimum. So the impedance value is root over R square plus XL minus XC the whole square. When XL is equal to XC, this term becomes 0, impedance is minimum. So the minimum impedance equal to square root of R square plus 0 square is equal to R. So the maximum possible current, I naught's maximum value will be E naught by Z minimum impedance. The minimum impedance comes when XL is equal to XC, that is E naught divided by R. This is the maximum possible current in the LCR circuit. So that means that happens when XL is equal to XC. When XL is equal to XC, the current is maximum in the circuit. So the circuit chooses maximum current when XL is equal to XC. That means XL is L omega, XC is 1 by C omega, and omega square is equal to 1 by LC, which means omega equal to 1 by root over LC. This is the resonant angular frequency. Resonant angular frequency, we can call it omega naught. So omega naught, resonant angular frequency is 1 by root over LC, or omega naught, 2 pi into frequency, we call it resonance frequency, equal to 1 by root over LC. So resonant frequency equal to 1 by 2 pi root over LC. So the resonant frequency is this. So the circuit offers minimum resistance in nu naught is equal to 1 by 2 pi root over LC, or omega naught equal to 1 by root over LC. In such case, current in the circuit is maximum, and that is equal to E naught by R. So series LCR circuit is also called a resonance circuit, series resonance circuit. That means when nu naught equal to 1 by 2 pi root over LC, the circuit resonates with the applied current. That means that it offers the minimum possible resistance and accepts maximum current in the circuit. So this is what series LCR circuit. The resultant thing is, let's summarize once again. The current, applied EMF will be E naught sine omega t. The resultant current will be I naught sine omega t plus or minus phi, where phi is given as tan inverse of XL minus XC by R, where XL is equal to L omega, XC equal to 1 by C omega, and the current is maximum when impedance is there. Suppose if you want to find out the maximum current in the circuit, equal to maximum voltage divided by root over R square plus XL minus XC the whole square, where this portion is called impedance. So E naught by Z. So what is the maximum possible current in the LCR circuit? The maximum possible current in the LCR circuit is E naught by Z minimum, the minimum impedance. So the minimum impedance offered by the LCR circuit will be equal to R. So, and we will discuss about the voltages measured in the subsequent video.